Let's discuss how the instrumentation of a process is documented. We'll go over process flow diagrams, piping and instrumentation diagrams, loop diagrams, and functional diagrams. Let's start with process flow diagrams. These are sort of the 50,000-foot view. They're an overall view of how things flow around in the process, primarily gases, liquids, that sort of thing. Now there are other flows to consider. There are flows of information and power, things like that. But that's not what a process flow diagram concentrates on. The point of it is just to understand what the thing is and how it works. So let's start with this simple one from the text, where we have an evaporator, a compressor, and a knockout drum, three primary pieces of equipment. And you might look at this, and let's start at the evaporator and say, well, we have steam coming into the evaporator. Well, not really. You got to understand how these diagrams work. The evaporator, you notice, has two rectangles on either side of it. Actually, that is a jacket all the way around, an annular region if you look at it from the top down, where steam is introduced into the jacket in order to warm up the evaporator. So apparently, maybe whatever's coming in here is, I don't know, maybe it's air and water, maybe there's some liquid in it, and the evaporator's job is to warm up that water so that it evaporates. Maybe that's what this does. Anyway, it's called an evaporator, and it has flow in from the bottom that's being processed. Now, the flow in from the left, that steam flow, is a flow that goes into the jacket and serves to heat up the evaporator, and then it comes out as condensate. When you have process steam, the energy storage that you give off is a phase change. It's a latent heat of vaporization. And so what that means is that it comes in as a gas, as gaseous water we call steam, and you don't want it to leave unless it leaves as liquid water, because you want it to give up all of the energy that it can, and it's primarily the phase transformation that's giving up energy. Anyway, so the fluid to be processed is coming in through the LV down at the bottom. So what is LV? Well, LV stands for a level valve, a valve that controls the level. Really, it's controlling the flow rate into the tank, but you notice we have an LI on the evaporator, a level indicator. And so what's happening here, actually this is probably a separation process, actually, where we're desalinating water. That's kind of what it looks like, because you notice we have brine flowing out of the evaporator as well. So if we had, say, seawater coming in through that level valve, if you know anything about thermodynamics, you know that it takes energy to separate things. So if you're going to separate some salt out, it's going to take energy to do it. And so, of course, energy is coming in via the steam. It's giving off energy to the seawater in order to boil off, I guess, some fresh water. Anyway, so the TT, the final thing on that evaporator, is a temperature transmitter. That's what that stands for, and TV would be a temperature valve, a valve there for controlling the temperature of the evaporator. Notice there's no control indication here. There's nothing to tell you if this is cascade controls or feedback control. Where are the controllers? They're not shown. That level of detail is not shown on these process flow diagrams. But anyway, so the stuff comes out of the evaporator, probably just essentially gaseous water, steam, and goes into the compressor, where the compressor compresses it, and then it goes on to what's called the knockout drum. So you see M there from motor driving the compressor. FT would be a flow transmitter of some type to measure the flow rate going into the compressor. And then in the knockout drum, why we need that, I'm not sure. I suppose here we're reducing the pressure and allowing the water to go into the liquid phase. It doesn't matter too much. You notice we have water coming out the bottom of that knockout drum. And then there's some other stream coming off to the right. You notice a PV, a pressure valve, PT, a pressure transmitter, so we're measuring the pressure in the knockout drum. I believe that the item on top of the knockout drum is a pressure relief valve. It's not a symbol I've seen used before for it, but it would make sense that if you have a compressed gas, you need some way of letting it go in dire situations so that the knockout drum is not overpressurized and fails. Anyway, TI would be a temperature indicator, LT is a level transmitter, and LG, well, we'll have to figure that one out later. L would definitely be level, but I can't think of what G. Oh, G would be gauge, of course. So a level gauge. So this would just be something that a user could go and look at and see what the level is in the tank. A piping and instrumentation diagram zooms in a little bit from the process flow diagram. It shows you more detail, and the focus here, the flow is still shown, but now we've got other signals as well. We have some dashed lines here, which actually indicate information flow. Now, depending on what type of valve FV42 is, it would depend on, that would determine the type of connection between FIC and FIC42 and FV42. Because if FV42 is actually a pneumatic valve, then we would use a different type of line. Apparently this is some type of an electronically controlled valve, because those dashed lines, the standard for that is an electrical signal. And we'll see more about the standard line types for piping and instrumentation diagrams later. Also, know one thing. Notice that piping and instrumentation diagrams have the short form of P ampersand ID, and that's probably there to differentiate between a P&Id controller and a piping and instrumentation diagram. All, both have P&Id in their names. So FIC, the flow indicating controller, number 42 there that you see, might be a P&Id controller. Notice it appears on a piping and instrumentation diagram, so a slight point of confusion there. Anyway, so we get to see more information here. We can still see the flow of the fluid going from the evaporator, but then it goes into this shaped thing, this sort of an hourglass shaped item. And what is that? Well, that's most likely a venturi tube. Venturis can be used to change the pressure of the flowing stream, because they neck down, so the velocity increases and the pressure decreases because of conservation of energy. And so if we measure the pressure in the throat of the venturi, the smallest area, we can actually, given knowledge about the venturi, we can determine the flow rate. Or really it's a pressure drop that's measured, but that gets transformed into a flow rate. So FT42 is flow transmitter number 42, and it's transferring information about the flow rate through the venturi coming out of the evaporator and going into the compressor. It's transferring that information electronically to FIC42, flow indicating controller 42. Notice the F stands for flow and flow transmitter, FIC. Both of those start with an F, indicating that that's the variable that's being controlled, or the variable of interest. However, notice that I is something that is somewhat passive. It's not an active thing, because what I indicates is that there's a view of it for the user, for a human being. This is not something that really has any effect on the automated control system, but I stands for indicator. It indicates to the user what the flow is. So that controller is controlling the flow, but it also has some type of display to show the user what flow it's measuring and how much it is. Now, PDT42, you notice it has the same number, the same what's called loop number, and the idea for that is that you want all the instrumentation that has to do with one control thing to be together, one area of the plant essentially. And so PDT number 42 would indicate a pressure difference transmitter or transducer. And basically what it's doing is it's measuring the pressure difference between 2 points. Now you'll notice that the 2 points that it's connected to are some lighter lines. They're not arrow-headed bold lines, they're lighter lines, but it's still a fluid connection to those points in the process. Notice that one point connects after the compressor and the other before, as well as FV42. FV42 connects there as well, but FV42 has the intention of having fluid flow through it, whereas the pressure difference transducer, you wouldn't have fluid flow through it, you're just trying to measure the pressure difference across it. And so what is the purpose of this FV42, for example? Well, FV42 is an unloading valve, essentially. If the compressor starts surging, it can damage the compressor, and so the point of FV42 is to open up and allow some of the output from the compressor to go back into the compressor. Now, this seems wasteful, but it's better than a messed up compressor. I believe what happens is when there's not a high enough mass flow rate, then the compressor can tend to surge, because it's kind of like a vacuum cleaner. When you turn on a vacuum cleaner, put your hand over the suction port, it sounds like the vacuum is working really hard because the speed of the motor goes up, but actually what's happening is the vacuum is not working very hard at all. It's just not moving hardly any air. So it's very easy for it to spin and spin faster. I think that's a concern with a compressor, because of course compressors operate at high speed, and so if they overspeed, then they can be damaged. Of course, surging indicates the idea that it's, surging. There's an increase and then often a decrease in flow, and that change in compressor speed can be damaging. Whatever the reason, we need this flow valve to unload the compressor, and so it doesn't destroy itself. TT41 will be a temperature transmitter that transmits information about the incoming stream temperature that's going into the compressor. TT43 indicates the outgoing temperature from the compressor. Of course, this is important because that difference in temperature indicates how much energy the compressor is putting into the flow stream. Most likely the steam that's going in here or through this would be an ideal gas in most of this process, and so knowing the difference in temperature between the inlet and exit would give you an idea of how much work the compressor is performing. You'll notice that these the two dashed lines coming out of TT41, TT43 go to an instrument that has a single rectangle around it. So TIR41 and TIR43 are actually housed together apparently in the same instrument, but they provide two separate functions. One function is TIR is a temperature indicating recorder, so it's recording temperature over time, which is a valid thing, but of course that's for the sake of analysis later by most likely a human being or computer. And the indication I is for a person to see at this moment what is the temperature coming into the compressor or out of it. But TIR 41, 43 are apparently the two temperatures being indicated and recorded within one machine. So maybe it's a strip chart recorder. Modern electronic strip chart recorders have multiple lines they can draw at the same time. Even older strip chart recorders had that ability. So this is probably two separate lines on one piece of graph paper or one screen over time, so that you can see how the temperature across the compressor has changed with time. Because really, often it's the difference between those two temperatures that is particularly interesting. And notice that not all the details for controlling the evaporator or the knockout drum are shown here, but usually piping and instrumentation diagrams are large documents that show all of the process and all the detail. Now, just like a regular mechanical drawing for an assembly or something that's being manufactured, a lot of times a piping and instrumentation diagram consists of multiple sheets. And the reason for that is because you just can't fit everything reasonably on one sheet, and often you want to analyze one particular area. Now, process flow diagrams and piping and instrumentation diagrams serve a very useful, many different functions. They're used during design to try and predict failures, and the effects of failures are very important. And so you can imagine if you have a whole piping and instrumentation diagram or process flow diagram, you can look at it and say, well, what if this pump here fails, or what if this compressor fails? What's going to happen to the process? Will it blow up? It's a good thing to know, right? Will something else be damaged as a result of this? Or what could cause, say, the compressor to fail? Well, what if flow valve 42 fails, the compressor starts surging, and it tears itself apart? Well, the root cause was flow valve 42 failing. And that can be very valuable to know. It can also be valuable not just in design of the plant, but in operation of the plant. These can be absolutely critical for troubleshooting, for just day-to-day operation, for locating things and understand how things work and how they fit together. Now notice that flow indicating controller 42 actually gets data from two different sources, from the pressure differential transmitter 42 and from the flow transmitter 42. So the details of what it does with those is not shown here. I mean, maybe it completely ignores the difference in pressure across the compressor. I doubt it, but that's possible. Maybe it's a cascade system. Maybe it's a feed-forward system. Who knows? All we know is that there is a controller there that gets input from two sources, so it's likely either cascade or a feed-forward scheme. But the flow valve is the final controller. And considering it, since the flow valve can't actually affect the flow coming through FT42, apparently something else is driving that, or the compressor is sucking it out, well, the flow valve 42 doesn't directly affect the flow measured through flow transmitter 42, at least not that I can tell. Now it's possible it could, because it could be that the only thing pulling stuff from the evaporator is the compressor, and so by controlling the flow valve we can, let off the pressure from the compressor and won't pull quite so hard, and that would decrease the flow rate through FT42. It just depends on how this is set up. So you'll notice that there are bubbles and lines in these diagrams, and many of the aspects of process flow diagrams and piping and instrumentation diagrams, as well as some of the other diagrams we're going to see, is actually controlled by the Instrumentation Systems Automation Society, also known as ISA. And so there, as a standards organization type body, the standard does change from time to time, and so you'll see changes in it, but generally it remains about the same because it serves an important purpose of standardizing communication about standard sorts of things, standard equipment, and often standard processes. So if you see a circle that's indicating, some type of transmitter or controller, and it has no line in it, that means that this is a field-mounted device. One of the examples I'll probably go back to is that of American synthetic rubber. A few years ago, the Society of Manufacturing Engineers chapter at our location managed to get a tour of the facilities where they were making rubber. It was American synthetic rubber. It's on the west end of Louisville. It was a very good tour, very informative. They take chemical feedstuffs and make rubber for Michelin tire. Been there for many years, and it was a really, really interesting tour. We got to see many different reactors, heat exchangers, loading, unloading of chemicals, conveyors that convey the rubber along after it's actually been made into rubber, reactor vessels, all sorts of very interesting things. And of course, there was instrumentation all over the place. So this is a plant that's been there for a long time, and so they've apparently added on and changed things, and they showed us their old control room and their new control room. Of course, the advent of computer and digital circuits and so forth has really revolutionized control, and this plant was probably built, I think, back in the 60s or 50s, something like that. And of course, it's been upgraded over the subsequent years. And so they took us to their old control room, and it had become sort of an auxiliary room. They still had equipment and instrumentation there, but anything on a P&ID that's in that room would be shown with two lines through it, as you see on the right. So there'd be some type of auxiliary location where these things are mounted on a panel, and either in the front, so solid lines would indicate that, or behind the panel, in the rear of the panel, would be indicated by dashed lines. Now, like I said, if it's field mounted, then it's something out in the process somewhere, and as we walked around, they had to have several acres of space. It was quite a trek to see all the equipment they had, but there were tons of field-mounted sensors for sensing temperature and pressure, and probably, analyzing the chemical compositions of things and so forth. But then in their main room, in their main control room, any instrumentation there would have been indicated on a P&ID with a circle with a single line through it. Again, solid line if it's in the front of a panel where you can access it, and a dashed line if it's behind. So that's the standard way that these bubbles and lines are used, and they're showing you information about where these various instruments are located. Now there's several different line types. You see three that are grayed out there. They're not part of the standard anymore, although they are still used, but they're not a standard. It used to be that electrical signals, there was a differentiation between continuous and discrete signals. Discrete signals had a slash through it, but any dashed line now can represent an electrical signal. But you see several different items here. We've already seen the process flow line, the bold line, and then we've seen instrument supply or process connection and impulse line, and those are lines of where, like with the pressure differential transducer, we saw a solid line that was fine, and so that was still a connection to the process, to the fluid of the process, but just to measure things, measuring impulse essentially. We saw some dashed lines, and those were all electronic signals. But one thing you'll see that's very common are things like pneumatic lines. So if you have a pneumatic valve, the line going to it will be solid, but will have slashes through it. Okay, so there's still apparently a distinction between continuous, which are typically 3 to 15 psi lines, or an on-off pneumatic signal where you have a backslash through the line as well. And you see other items here. I don't expect you to memorize all these. Part of the reason for having all these in the slides is for you to go back and find them easily. They are, of course, pulled directly from the text, so you could go there, but the text is, 1,000 or so pages long. It's easier to go back to the slides and find them, so you can go back and look at this and see what an unknown line indicates by its line type. Now, the way that the connections are made to the piping, because typically we're talking about piping in these things, that's why it's piping and instrumentation diagrams. The things that go through them are fluids, so gases and liquids, and you can connect to those in several different ways. There's threaded connections. Those are very common, where you have pipe thread and you thread a sensor into something. You can socket weld things. There's flanges. There's all kinds of different ways. And again, this is more for your benefit, just documenting the different standard types of connections so you could recognize them on a P&Id, or at least refer back to this and see what the particular connection type illustrates. Now here's some more details on instrument bubbles. We've already seen the circles and understand the various differences between the line types. But then there's also shared instruments, and we've seen a shared instrument where we had a rectangle around multiple instruments, and so you see that there with a box around it. If you have a computer that's part of the process control, then that computer should be indicated by a hexagon. And if it's some type of logic operation, then you use a diamond for that. So these are instrument bubbles that are also standardized. Now let's get into a little more detail. Valves are extremely common on piping and instrumentation diagrams, because how do you control the flow of fluid? Well, with a valve. That's basically the way you do it. And there's many different types of valves. Just a generic valve looks kind of like a bow tie. You see it there on the upper left. One of the common things you'll see is a bow tie with a stem coming up and a hat on the top, sort of like the pressure regulator you see down there, but without the line going from the top of the hat down to the body of the valve. That would be a pneumatic valve. That's a very common symbol for a pneumatic valve. The pressure regulator valve, though, is shown with that line from the hat going down to the body of the valve, the bow tie, to indicate that the pressure is being sensed at the valve, and that's what adjusts the whatever type of adjustment there is on the valve to control it. So again, we're just more keeping track of all the different types of symbols that are available, because there are many. You see examples of ball valves there. You may have dealt with some. A globe valve is another common type, and then butterfly valves. If you have ever had a car that had a carburetor in it, then you probably had a butterfly valve in order to control the throttle. Even if it didn't have a carburetor, a lot of all the engines I know of still use a butterfly valve to control the airflow into the engine. There's another type of valve there, an angled valve. You notice that 3 over 3 down, where the bow tie is sort of broken to indicate that it's a valve at an angle. And you've got three-way valves and all sorts of things. And the valve status may or may not be shown on the piping and instrumentation diagram, but you'll notice that the standard for that is that if the bow tie is not filled in, then it's open, and if it's filled in, then it's closed. It's blocking fluid. But again, this is not all that common on a piping and instrumentation diagram, at least not the ones I've seen. Now, going back to valves, really the last slide talked more about the valve body, but if we get into the thing that moves the valve, the actuator itself, then a diaphragm valve, as I said before, is a very common one, the one on the upper left. On the other hand, you don't have to have air move the valve stem in order to control the valve. You can have an electric motor control the valve stem, and that's what's shown next. You can, of course, have a solenoid to control the valve, and a solenoid is just a metal rod, essentially, that can be pushed by a magnetic field. It has to be something that you can, that's ferromagnetic, so that it reacts to a magnetic field. And if you have a coil of wire and you put a ferromagnetic rod in it, you can push and pull that rod just by changing the direction of current going through the solenoid windings. And so you can use that then to open and close a valve. And it used to be that solenoid valves were all on-off type valves. The valve was either opened or closed. One of the big manufacturers of that type of valve is ASCO. Red Hat is their line of valves, and these are very recognizable because the solenoid itself is usually green and there's a red button on the top, probably holds the thing together or something, but they're sort of a red hat on top of it, so they're called Red Hat valves by ASCO. Many years ago they introduced a proportional valve where instead of that rod being just either pushed all the way in or pulled all the way out, open or closed, what it did was you could actually turn the current on and off to the winding very quickly and float the spool within the valve, and so you had a valve that could be partially open or partially closed, which is a great advance over just a diaphragm valve. Diaphragm valves have their own sets of problems, and if you can just use electricity instead of any air, it can simplify the process for some applications. You can have a piston activate the valve, a hand jack with a diaphragm, an electric motor with a hand jack, so in other words you can manually override the valve, or you can simply have a hand valve, a manual valve. So there's all these different items. Positioners are really important because these valves tend to stick, and so a positioner is something where it automatically detects the current position of the valve stem and how far it's into the valve, in other words how open or closed the valve is. And based on the command that is being given, it positions it so that it's actually following the command. It's kind of hard to understand until you've dealt with them, but basically think of a diaphragm valve. You're putting air pressure in it. Well, there's so much friction on the stem that there's a lot of hysteresis, there's deadband, there's all kinds of problems with these valves. And basically the problem is you're putting pressure in it doesn't go until it finally slips and then it goes too far. So positioner helps in controlling those types of valves. Now when selecting a valve for a process, the failure mode of the valve is really important. Remember, when you're studying the P&Id or you're designing it, it's important to know how things are going to fail and control how they fail so that they can fail in a safe manner. If you have some type of cooling fluid going into a reactor jacket, you probably want that valve to fail open so that cooling fluid can continue to flow around the jacket. You don't have some runaway exothermic reaction in a reactor vessel. Rather, you have cooling water that can continuously flow, even in the case of a failure. So failing open is an important valve attribute, and so you see in the upper left box how a fail open valve is indicated, either with the letters FO or with an arrow pointing up towards the actuator. And of course fail closed is the opposite. There's fail locked, where the valve can't be moved. Fail indeterminate means you don't know how it's going to fail. Then there's also fail last or drift open, and this is just it fails based on however it was open or closed, and it slowly drifts open. And then there's the opposite where it drifts closed, and you can see the standard symbols for those. There's many different things that have to be controlled, and the most common ones are temperature, flow rate, and level. Those are probably the most common items that have to be controlled and that are shown on a piping and instrumentation diagram. So we see several different symbols for indicating different types of liquid level measurement devices, and one way to measure liquid level in tank is by pressure. And so even though if you look down at the hydrostatic first item in the middle there, LT, the level transmitter, is probably working based on the pressure difference between those 2 points. But even though it's a pressure that's being measured, it's still an LT, a level transmitter, because what you're doing is taking that pressure signal, inferring the level, and then controlling the level. So a lot of times these devices work off of some variable that you may or may not know what it is, but the purpose of it is what's really shown here. And of course there's many different ways of measuring level in a tank. You can bounce a radar or a sonic wave off the top of it, or even a light beam, a laser, and measure different properties of the reflection to figure out what the level in the tank is. But you see the various symbols there and the connection between the level transmitter and the vessel itself. Of course, there's many different types. There's bubbler methods where you literally bubble usually air through the liquid, and based on how deep the liquid is, the rate at which the bubbles come out will change. As the liquid level goes up, the rate of bubbles coming out slows down. And there's capacitive methods and so forth. Capacitive method is just a capacitive type sensor where the level in the tank changes the capacitance of essentially what becomes a variable capacitor with the vessel and the sensor. But that doesn't really matter. What matters is that there's many ways to measure the liquid level in a tank, and they can be indicated as shown here. Flow measurement devices, another very important parameter to measure, can be measured many different ways. You'll notice the V cone over there, the Venturi, last one on the right in the middle. We've already seen an example of a Venturi. There's also turbines that I've worked with before. That's third over, two down. And target types, flow nozzles. We'll see a flow nozzle here in just a minute. But there's many different ways to measure flow rate, and this is just some of the various technologies. Again, I'm not trying to go through every single one of these. This is more for your reference. But notice the orifice plate one. We'll see an example of that later as well. Process equipment. One of the problems with trying to show you all these symbols, number one, it's boring. Number two, a lot of times there's custom equipment required for each process. So a process is a little different. You know, sure, most processes have heat exchangers or pressure vessels or pumps, but there may be a special type of pump that's necessary, or a special type of piece of equipment that is unique to that process and not common. So here are some of the common ones, but there can be many other things as well, and you just have to know from the context what it is, or be able to look up what that symbol means. And as you move away from these standard symbols, you'll find more and more variety in the way that custom equipment is shown. But you see a jacketed vessel there, you can see a mixer on the bottom row, and sometimes these things are put together. For example, you could put a mixer with a jacketed vessel and make a stirred tank reactor. So that's something where you have some reaction progressing within the vessel, but it needs to be mixed up so that the reaction proceeds equally everywhere, or to increase the speed of reaction, or for some such purpose. Here are several different electrical diagram symbols. These are not things, well, they're kind of like what you might find on a schematic, but there's many other symbols that are common for process flow, well, not process flow, but for piping and instrumentation diagrams. And some of the things you wouldn't normally see on an electrical schematic. You've probably had a fluid power class. If you haven't, fluid power, whether it be hydraulic power or pneumatic power, have their own sets of symbols, and these can be included on a P&ID. Although there's a lot of variety within those two sub-disciplines, and these are just some of the standard symbols that you might or might not see on a P&ID. Now, the identification tags, usually the first letter indicates what it is you're interested in, the reason for that particular instrument. And so, for example, if you have an F, we've already seen Fs, well then that indicates flow. All right, so that's what we're interested in, is flow. Now, these letters can be used as modifiers. Remember, we had a PDT, a pressure differential transducer. So P is the variable we're interested in, right? It's the pressure. D is a modifier, which means differential. So we're taking the difference between two different pressure points. And then T, the last letter, indicated transmission. We'll see that here in just a moment. But if you wanted to measure something like temperature, well, then you're going to use the variable T, or the letter T, as the first letter. So a TIC would be a temperature indicating controller. Now notice that there's no modifier here for I. It takes a little bit of time to get used to reading a piping and instrumentation diagram. So the I is not a modifier of, say TIC, temperature indicating, what I say, controller, that would work. The I doesn't modify temperature, it just indicates a function that particular instrument includes. And of course the C is not part of it. So the first couple of letters are going to be a variable and a modifier, or maybe just the variable that's of interest. So then if we have a passive function like indicating, then you see that I means indicate. So a TIC, temperature indicating control. The active function C then is control. So temperature indicating control. is a controller that controls temperature and shows the user an indication of the temperature measurement. Many other examples. We saw PDT before, as I said, pressure differential, and then T, transmit, active function. What does it do? Well, it transmits that, or transducer, or whatever you want to call it. There's a difference between the two, so technically it is a transmitter. So again, these identification tags are to help you along in identifying the various tags and what they mean. So here's some examples. AIT, Analytical Indicating Transmitter. The A is what we're analyzing, so maybe this is measuring the concentration of some chemical in a flowing stream. In my boiler where I burn wood to heat my home, I don't really like burning wood. I don't like shoveling wood into the boiler. I would like for the boiler to burn it as efficiently as possible. That's why I bought the type of boiler I chose. So if I wanted to improve it and instrument it, maybe what I could do is take an analytical device of some kind. I'm sure there's one out there where I could measure, say, oxygen concentration or carbon monoxide, or maybe there's one for long chain hydrocarbons, in other words, smoke, so that this sensor could tell me how much of that is in the exhaust, and maybe I could control the airflow rate, say, into the boiler to try and minimize the carbon monoxide coming out, right? Because carbon monoxide is unburned fuel, so is long chain hydrocarbons. I don't want any of that to come out. I want it to all react and burn. That would require some type of gas analysis. And maybe there's something available, maybe there's not, maybe it doesn't make sense in my case to do that. But there are plenty of processes where measuring the chemical species and doing a chemical analysis is worthwhile. So I would be that it indicates, and then T is transmitter. So it's measuring chemical concentration, for example, as your author gives, an oxygen concentration analyzer with a built-in display of the oxygen, and then it transmits that information on for most likely the sake of control. And then we've got ESL. This is not English as a second language. E, usually we talk about electric potential when we're talking about electricity and studying it. So what it's doing is it's measuring voltage, right? It's measuring the electric potential in volts. And then S stands for switch, L is low. So this is something that switches when the voltage is too low. Let's jump down to FIC, a flow indicating controller. So I means that it's an indicating thing. F, of course, is flow, and C is controller. HC is a hand controller, so maybe it's something that's a valve. Probably would be a hand valve, then HV. Or some other device that allows a human being to use their hand to control part of the process. Here's some more examples. PIT, a pressure indicating transmitter. We've already seen a PDT, a pressure differential transmitter. What else might be interested in here? VSH, next to last. Vibration switch high, so it switches based on high level of vibration being sensed. TKAH, going about at the middle of this. The temperature rate of change alarm. So K stands for the rate of change, and it alarms on high. Now let me show you a sample P&ID that was near and dear to my heart. I worked for Amatrol for several years after college, and I was exposed to some of these pieces of equipment. As a matter of fact, the equipment on the left and the right here, you can see there's 3 items. Those were things that were designed by someone other than myself. I designed the one in the middle. That was one of my projects. I think I spent about 6 months on it, something like that. And of course what I did was I used the same basic frame and cabinet and everything, and then designed a different process. The process on the left, that's a process control system. These are actually for training people. And they're nice things, but they're more for technicians than the level you're working at. Nothing wrong with them, it's just that's what they're for. And what the one on the left does is it teaches you how to control flow rate and level in a system. And so there's a tank on the left on the upper side that allows fluid to flow down into the lower tank, and then there's pumps and things to move it sort of in a counterclockwise circle. And so you can control the rate of flow. There's a little instrument tucked up under the cabinet, sort of in the middle. It's blue and has some lines, clear lines coming down from it. That is a flow measurement system that measures flow by a pressure drop across some type of a flow restriction. And then you'll notice more to the right under the The cabinet is a valve. It's a flow control valve. It's got a brass body and a dome at the top, sort of. That's the diaphragm that you can apply air pressure to and push the valve up and down, insert and remove the stem to control the valve and control the flow through it. The one over on the right is the thermal process control system. Why they have the number T55, 53 for that, and 52 for the process control system, the temperature, not the temperature, but the level and flow system, I don't know. Don't know why they came up with those numbers, but those two, the T55, 52, and 53, were, as I said, designed before I got there. The 53's job was to teach students how to control temperature. And it also flowed in sort of a counterclockwise fashion. Of course, me being a chemical engineer, they asked me to design something to control pH. pH is a measure, if you remember from chemistry class, of the hydrogen ion concentration. And that's basically acidity, or how basic or acid something is. And wastewater treatment's a very common application for controlling pH. When you treat wastewater, one of the most important things to control, besides, of course, whether or not there's alive stuff in it that can cause disease or not, but one of the other really important things to control is the pH. Before you release wastewater out into the environment, you have to control the pH, because anything too alkali or too acidic will devastate the local environment. So you don't want to do that. You want it to go out pH neutral, so a pH of 7. And I designed mine to go sort of in between the 52 and 53. The 52 and 53 were originally designed, you can see the pipe stubs there, they were designed to just screw in together so you could have the two together and learn to control temperature and flow and level all at the same time. And mine's designed to go in between those two systems and control pH while you're controlling everything else. It flows in a generally counterclockwise setup, so you could have any one of these individually, just cap off the stubs at the end and have counterclockwise flow. So we'll look a little more detail of these. These are the P&Id diagrams of all three systems in the same order as I showed you before, as the pictures of the actual devices. And it's the piping and instrumentation diagrams for each one. Now you can't really see them here, so I'll have to look at them in detail individually, but you can imagine that you can see how all these would connect together with the pipe stubs, as I mentioned. The 52, if we start on the left, you can see the upper tank and lower tank. You can see the piping, and it's probably a little too small to read, but if you zoom in on the upper right, for example, you'd see plant air coming in from the right, and of course the line type used there indicates a pneumatic line, which makes sense. You see PC100, PI100-C. What are these? Well, P would be pressure, so PI would be a pressure indicator. PC would be a pressure control of some type. Now, in this context, this is not an automatic control in the sense that it's some type of a PID controller you're going to tune. PC, what they mean here is this is probably just some type of pressure reducing thing. So you would likely set it with a hand knob so that whatever pressure you want is indicated by PI 100-C, and that takes plant air down to the pressure that's needed for the process. And so IY is something that likely would be measuring current, because I is the most common thing is current. Now, why they used IY here, I'm not sure. I'm beginning to forget some of the details of these various systems, but I do know FIC 100 would be a flow indicating controller, and that thing's job is to control the flow rate going through the piping that FCV is connected to, the flow control valve, FCV 100. Now notice these 100s all go together. In piping and instrumentation diagrams, those numbers would often have not just a 100 in them, but a 1 and then some other numbers. But generally the 1 indicates that they're all in the same area of the plant. They all work together somehow. Of course, there's exceptions to this, but generally I'd expect to find all the 100 series in one area of the plant and generally working together. So FIT is a flow indicating transmitter. That's that little Rosemont transmitter that I talked to you about a minute ago, and then FE would be a flow element. Well, actually it may not be, because the flow element shown here is a turbine type meter, something where you have positive displacement as fluid flows through it. It rotates the turbine, and if you count the number of blades that go by or the number of ticks, you can indicate the flow rate. So this is a flow indicating transmitter, and what they haven't shown here is how this is electrically connected back, most likely to the flow indicating controller. So there's some electrical system or electrical lines missing here in this. If we look at the lower right hand side, you see FI, a flow indicator. This is not something that has any electrical connection, it's just a rotometer. And a rotometer is really just a angled tube with tick marks on it that you calibrate. And as fluid flows through, there's a little weight that's raised up, and the faster the flow, the higher the weight rises. You can just read it off on the scale. HV would be a hand valve, so the user could close that valve and choke off flow if desired. FV100 is a flow valve, although I thought they already used a flow valve. Maybe not. Anyway, so you can see how these various items work. There's a solenoid valve, SV100A, and pressure indicator 100A and 100B. And so that would just indicate the pressure before and after this valve loop. Over on the left-hand tank, you can see the reservoir tank with a water pump, a hand valve for draining, and the upper tank has an LET, LSH, 200A, 200B. What is an LSH? Well, a level switch high. Now, did they intend to have one as level switch low and one as level switch high? I don't know. Like I said, this is not one that I designed. Maybe there were two different types of level switches, so students could see a couple of different types of level sensing technologies that are both switches. LET, L would be level, T would be transmitter. The E, I'm not sure. We'd have to go back and look and see if that's a modifier or if it's a secondary function of some type. You see hand valves, solenoid valves, and so forth at the bottom of the tank. The system all the way on the right, the 53, was the temperature controller system. It's a little more complicated. If we go through it, there's some interesting things. We can see on the lower right of the diagram, we can see plant air coming in to PC 1000, so pressure controller 1000, a pressure indication, so probably just a little gauge to indicate the pressure, and then a flow indicating controller, because this system could also control flow, and it controlled flow for the sake of really just controlling the rate at which heat is added or removed from this system. I don't remember which. But FI700B is just a flow indicator, another rotometer. HV700 is a drain valve, so that this side of the system can be drained. One interesting thing about this trainer is there were two separate fluid loops, and they were connected together by a heat exchanger. Now you'll notice when we get to it that the standard symbol for heat exchanger was not used in this P&ID for whatever reason. FCV700 is a flow control valve, and you'll notice that it's a three-way valve. So that's kind of interesting. There's a hot water pump there for use as well. And you can see that the direction of flow being clockwise in this loop is indicated by the arrows. Now if we continue to the lower left side of the piping and instrumentation diagram, you can see there's another pump on the other side. This is the other fluid loop, and this is the side of the fluid loop that would interface with the other two process control trainers I showed you. Now again, I didn't design this P&ID, and I didn't design the last one. I did design the next one for the 54 for the pH control trainer. But you can see other items here. There's a chiller, which technically is a heat exchanger, although they're showing it as one item. Technically it'd be a heat exchanger along with a compression, a compressor, and other various equipment, but they're just showing it as a chiller, a box, and what it does is cool down the flowing stream, and that's all we really care about here. They didn't have to show all the guts of that chiller and how it worked. So you can see different elements here as well, and probably have a good idea. FI is flow indicator, TI temperature indicator, FV flow valve, TE temperature element, so that's something that's measuring temperature. But why, I don't know why they use TE if they weren't either indicating it or transmitting it onto something else, but there it is. If we look at the upper left side, zooming in on it, we can see a heat exchanger. Again, not a standard symbol for that heat exchanger, but there it is. And FS is most likely a flow switch, FS500, and all of these we've seen before. TE would be temperature element. Again, I don't know why they don't include something about transmitting it or indicating it. And if we look at, where are we, upper right side, you see that there's an option. When a customer bought the 53, they may or may not have opted for a flow measuring element, FE700, and a flow transmitter, FT700. That was an option that could come with the system if necessary and didn't have to. Now let's look at the one that I designed, the 54, the analytical process control trainer. As I said, what we were analyzing was pH. When you do chemical analysis, there's all kinds of things that can be analyzed. Then you're in the world of chemistry, which is a huge, obviously, area. But if we look at generally the right-hand side, the way I set this up was there was a reactor tank sort of in the middle of the system. You can see that shown here. It had a stirrer in it to make sure that the acid or base, in this case the acid that's being added, could be mixed in. And the goal of the acid was to actually neutralize what came into the reactor tank, because I made sure that something more alkaline, more basic, came into the tank and needed acid to even it out and come out to a neutral pH of 7. But you can see the check valve there, and the check valve just prevents the stuff in the tank from flowing back up into the feed, the acid feed. Now we just used vinegar or acetic acid as our acid feed. You'll notice that there's a pump just below the acid feed reservoir. It's a metering pump, and the purpose of that metering pump, which it's a metering pump we know because of the adjustment on the right side, it looks like a little hat. This metering pump, what it would do is meter out a very precise amount of acid in order to get the right amount in the tank and neutralize the flow. There was a bleed port so that if we needed to bleed off the system, we could by changing the three-way hand valve there. And like I said, the check valve leading into the reactor tank, its purpose was to prevent any backflow up into the acid. There's a water pump. That water pump that's shown there was actually something I had to, that was an expensive part of the system because I had to make it, or I had to buy it out of stainless steel or brass, and stainless steel was cheaper. So I went with stainless steel, and it's mounted up under the reactor tank if you look at the photo of the 54. That leads into a solenoid valve, SV, and then there's a low point drain over on the right that's also a hand valve. But normally you wouldn't have that low point drain open, the fluid would go up and to the right. And you notice there's a little loop there with 3 valves on it. There's a hand valve at the bottom, there's a hand valve 1400C, hand valve 1400D, and then a PHIT and PHE. You might wonder what those are for. Well, you have to understand something about analyzing pH. pH sensors, or the pH element, so you notice a lowercase p with an h together, those two indicate the variable being sensed. P by itself would be pressure, and it would be an uppercase thing. So like I said, there's some interpretation, because a lot of times you'd expect that second letter to indicate, a modifier of the first, but instead here pH goes together as the item being sensed. So PHE 1400 is a pH element, and PHIT is a pH indicating transmitter. Now, something you need to know about these sensors, these pH elements, is that they're kind of like batteries. They go bad after a certain amount of time, and you have to replace them. Well, if you're operating a wastewater treatment plant, you probably can't shut off thousands of gallons going through per minute or per second, and so what you've got to do is somehow have a bypass, and that's the way I set this up. So there's a bypass network where in normal operation HV 1400E would be closed, but to change out the and HV 1400C and 1400D would be open, but to change out the pH element, the sensor itself, what you would do is you would open HV 1400E and then close off C and D, so that the pH element is isolated from the rest of the piping line. Then you could just remove the element and replace it, and then do the opposite again, open up C and D and then close off E, so that the fluid stream goes through the element and its pH is measured. The flow then continues on and either goes up through FI 1400 and FV 1400, or it connects to the 53 on the right hand side with those stubs that go off to the right, and then you'd close FV 1400. FI is just another rotometer, so you can see the flow rate visually, but then it wraps around, the flow wraps around and goes, continues across the top, bypassing the acid feed. Of course, the lines indicate, as they would on a schematic, that the feed from the acid jumps over. I just didn't have room to put it down lower, and besides, physically it's above that. So I was trying to indicate that the acid tank was above that horizontal line. If we look at the left-hand side of this, there is a base feed. Now really the base feed was down lower. It was not above that upper line. I should have probably tried to squish it all together. I think I tried and it was just too much, but anyway. Standard stuff we've seen before: HV for hand valve, FCV, flow control valves, FIT, flow indicating transmitter, FE flow element, and so forth. Nothing really all that interesting. You notice there was an option for a pH IT, a pH indicating transmitter, and a pH element in the tank itself. There's a high switch based on level and a low switch based on level. I probably got those backward. It probably should be level switch high and level switch low, but that's my mistake. There's also an option for measuring the pH before the flow comes into the tank. But then we see a very interesting thing we haven't seen before. We see what's called an inductor pump. What's that? It's either an inductor or an injector pump. Well, it's a very simple pump, and actually what it does is, really it's more of a turbine that goes in the stream, and that turbine then drives a pump. And what happens is it injects a certain percentage of flow. So you can change the setting on the inductor pump so that, if you have 10 GPM going through the main pipe, it adds, say 1 gram every 10 GPM, and it is a continuous flow. So what we were doing here was simply making the wastewater, right? We were adding baking soda, sodium bicarbonate, in order to make an alkali solution that needed acid to neutralize it. And we just wanted the baking soda flow. And it wasn't just baking soda, it wasn't the powder, it was a liquid, baking soda already dissolved in water. But we wanted to make it so that the user could set a different, maybe the teacher could set a different concentration of the base, and then the students could program the P&Id controller and instrument it, make sure it all worked, so that they didn't know how bad the feed coming in would be, how alkali it would be. The teacher would set that, and then they could see if their system would work and neutralize it. But you notice that's not a standard symbol, right? It's like two pumps put together, but that's the best symbol I could find at the time. Maybe there's something better. Maybe there's a standard symbol I didn't know about, but I was trying to indicate something unique. Remember I said often on P&Ids, you need a symbol that is very unique, and it's specific to the particular process. Well, there's an example of one.